Hello, welcome back to another CHEM271 tutorial. This is the final tutorial I will be making for CHEM271. This will be going over the second practice final problem set. These will be completely different problems from the first practice final. They will cover all of the topics in metabolism, glycolysis, gluconeogenesis, glycogen, citric acid cycle, electron transport chain. All right, so question 1A is asking, how is lactate converted back into glucose? So lactate is made as a result of fermentation. So fermentation converts pyruvate into lactate. Why does it do that? It does that because glycolysis builds up a lot of NADH, and in order for glycolysis to run, that NADH needs to be converted back into NAD+. So through fermentation, the NADH can be used up, and this happens without oxygen in the cell, because without oxygen, the electron transport chain cannot run. The cell cannot make a lot of ATP. It can only make ATP from glycolysis. So this is a way to keep glycolysis running by ensuring that there's no buildup of NADH. Okay? But when there is oxygen in the cell doesn't need all this lactate anymore, so that it can turn the lactate back into pyruvate, and in doing so, it actually regenerates NADH. Then the pyruvate can be converted back into glucose through gluconeogenesis. All right? But why exactly is oxygen required for this? So the main reason is because once oxygen is back, if there's a buildup of lactate, that lactate can be converted back into pyruvate, and the pyruvate can do something else. But there's another reason why oxygen is required for this. Oxygen indicates that the electron transport chain is active, which leads to ATP generation. So why exactly is ATP needed for this? It's because gluconeogenesis, remember, requires a lot of ATP to make one glucose. So lactate to glucose uses actually 6 ATP per glucose, right? However, this will lead to no net NADH loss. So why? So we know that 1 NADH will be made from the conversion to lactate to pyruvate. And we know we need 2 pyruvate per 1 glucose, right? So we have 2 times 1 NADH made per pyruvate. And then how much NADH is used up in gluconeogenesis? So it is 2 NADH used per glucose. So this can also be thought of as 2 NADH made per glucose. And this is just 2 minus 2, so 0, no net NADH loss, right? 2 NADH are made per glucose, converting lactate into pyruvate, 2 NADH used per glucose, and this is in gluconeogenesis. All right, so next question. All right, question 2. Malonate inhibits succinate dehydrogenase. Succinate dehydrogenase, of course, an enzyme in the citric acid cycle, converts succinate to fumarate, right? What kind of inhibitor is this? So let's look at the structures. This is malonate, and this is succinate. They look pretty similar, and because they look similar, we can say this is probably a competitive inhibitor. Why? Similar structures. Why does that matter? Because this means that if this is what needs to bind to the active site, then this can also bind to the same active site because it looks similar. Okay, it's a similar structure, it can bind in a similar way to the active site. However, no reaction occurs because if you remember what this reaction here is doing is it's turning this here into a double bond. So essentially, this doesn't have 2 carbons that can form this double bond here, so malonate cannot be converted into anything, it cannot react. So it binds to the active site, but it does not have the CH2 needed to actually convert this into CH. Right. This trans double bond here. Okay. So how exactly could you prove this hypothesis that this is a competitive inhibitor? We have to determine Km and Vmax. So we find Km apparent and Vmax apparent, right? So these are the new Km and Vmax with the inhibitor. Okay? And to do this, we determine Km and Vmax without the inhibitor, we add the inhibitor, then we redetermine the new Km and Vmax, which is Km apparent, Vmax apparent. And if this is a competitive inhibitor, what we find is, so if it's competitive, what we find is that Vmax is equivalent to Vmax apparent, right? Because if you add enough substrate with a competitive inhibitor, the substrate outcompetes the competitive inhibitor, and you get the same max velocity. The enzyme active site isn't altered at all. However, we will also see Km is less than Km apparent. Why? Because with the inhibitor, it takes more substrate to fill 1/2 of all enzyme active sites with substrate, because those active sites are also going to be filled with inhibitor, all right? So if you observe these trends, you can then confirm that malonate is, in fact, a competitive inhibitor. All right, question 3. So this question's asking about Leber's hereditary optic neuropathy, which is the inability to transfer electrons from NADH at complex 1. So the first part of this question is asking, why is this non-lethal? And the answer to this is because you can still generate the proton gradient in the electron transport chain from FADH2 at complex 2. So FADH2 at complex 2 can be used, and this allows for ETC to keep running. Okay, so now the next question is a bit more difficult. So how much ATP is produced? So we know that we are getting 4 ATP per glucose from glycolysis and citric acid cycle. We know we are getting 2 FADH2 from the citric acid cycle, so 2 FADH2, which this is 1.6 ATP per FADH2, which is equal to 3.2 ATP per glucose from FADH2. Marker dying. It's fine. And then the last thing to consider is that the NADH in glycolysis actually can make it into this, because remember, NADH glycolysis, if they use the glycerol 3-phosphate shuttle, let me get a new marker, with the glycerol 3p shuttle. So the NADH in glycolysis can be converted into FADH2. Okay? So that means we get 2 NADH in glycolysis, which get converted into 2 FADH2, which this is another 3.2 ATP per glucose, and the grand sum of this is 4 plus 3.2 plus 3.2, so this is 10.4 ATP per glucose. Okay, and we know that this is far less than the normal 30 ATP per glucose, roughly 30. Okay, so because of this, because we're only getting the ATP from glycolysis in the citric acid cycle, from FADH2, and from the NADH in glycolysis, none of the NADH in the citric acid cycle can be used because complex 1 is inhibited. So the electrons they can only enter at complex 2 from FADH2. Essentially, we just make a third of the ATP. So it's pretty bad. The other part of this problem is how does this impact the citric acid cycle? So the main thing here is that we have high NADH concentration now. Why? Because none of that NADH in the mitochondria generated from the citric acid cycle can be used up because complex 1 is inhibited. 1. All right. So what is the impact of high NADH? So this has to do with regulation. So remember, this will inhibit PDH, pyruvate dehydrogenase. It will inhibit isocitrate dehydrogenase and 3-alpha-ketoglutarate dehydrogenase. And this will all happen allosterically, right? So allosteric inhibition of these enzymes. And what that ultimately does is this will slow down the TCA cycle. Why? Because with these key enzymes of the citric acid cycle being less active, it means that there's just going to be less carbon flowing through the citric acid cycle, so less overall. So overall, you make a third of the ATP and you produce less from the citric acid cycle overall because of the NADH buildup, and that means even less ATP really. So yeah, but it's non-lethal because you still generate some ATP. Question 4, this one is about thermodynamics. So calculate delta G for glycogen N plus Pi turns into glycogen 1-phosphate plus glycogen N minus 1. So this is the reaction catalyzed by glycogen phosphorylase, right? So essentially we're given 2 reactions with 2 delta Gs. So this is something that you'd see in like Gen Chem, but applied to biochemistry. So water plus glycogen turns into glucose plus glycogen N plus 1, and water plus glucose 1P turns into glucose plus Pi. So essentially what we want to do is add these reactions together. So essentially what we are going to want to do is flip this reaction, okay? We want to flip this reaction and flip its delta G sign. Why? Because doing so means that glucose will cancel, water will cancel, and we'll be left with the original reaction. So if I erase this and rewrite it the other way, sorry, it can be difficult to erase. So the other way, we have glucose plus Pi turns into glucose 1P plus H2O, and then the delta G, we flip the sign, so now it is positive 5 kcal per mole. And now we can see that glucose here will cancel, and that water will cancel, and then what we'll be left with is glycogen plus phosphate produces glycogen N plus 1 plus glucose 1P. So if we add those together, we get the original reaction. So that's why I flipped the second equation, because when you add this normal reaction with this flipped reaction, they add together to get this top reaction. And because of that, now we can add their delta Gs. So we get delta G is going to be equal to negative 4.3 kcal per mole plus 5.0 kcal per mole. And what do we get? We get plus positive 0.7 kcal per mole. So this is a positive delta G, meaning that this reaction is not super favorable. It needs some input of energy or some form of coupling to happen. Part B, calculate K at equilibrium. So we are given delta G equals delta G standard plus RT ln K. we know that delta G is going to be 0 at equilibrium, so we can rearrange this to delta G standard is equal to negative RT ln K. If we want to solve for K, we divide both sides by negative RT and then do e to the both sides, so we get K is equal to e to the negative delta G over RT. Okay? And we know that R is going to be 1.9859 times 10 to the minus 3 kcal per mole Kelvin. Notice we're in kcal, not in kilojoules, so R changes with the units. T, 310 Kelvin, that's 37 degrees Celsius plus 273 is physiological temperature. Okay, so now plugging this in, we get K is equal to e to the negative, negatives from here, negative plus 0.7 kcal per mole, all divided by 1.9859 times 10 to the minus 3 kcal per mole Kelvin times 310 Kelvin. And what do we get when we plug this into our calculator? We get K equals 0.32. So we know K is going to be less than 1, which means that the concentration of the reactants is going to be greater than the concentration of the products. So the reaction won't be super favorable. A lot of the reactions will still be there. Why is the reaction not that favorable? Because we have a positive delta G. All right, next question. All right, question 5. What happens when you add the following to a mixture containing mitochondria, NADH, and O2? So we are looking at O2 consumption here on the y-axis and time on the x-axis. So part A is asking what happens when we add ADP and PI. Okay, so we have mitochondria, we have NADH, and we have O2. So what's going to happen when we add ADP to this mixture? So we start out with no O2 consumption, and then when we add ADP, what happens, and PI I guess, we start seeing O2 consumption going down. Okay, it starts to decrease. Why? Because we know NADH plus ETC, what are these going to do? These are going to make an H plus gradient. All right, and we know that ATP synthase runs off H plus gradient. So because essentially what's happening is NADH is constantly building up the H plus gradient, ATP synthase will constantly be using up that H plus gradient. So the cell will continue to generate the H plus gradient. Or well, I guess these aren't cells. So mitochondria. So we'll keep doing it. H plus gradient will be continuously made by the electron transport chain. So the electron transport chain will still be active, and this leads to O2 consumption. Remember, O2 consumption is by the ETC, specifically complex 4, right? So when we add ADP, this essentially allows for the dissipation of the H plus gradient, and then once that happens, the electron transport chain can sort of continue to be active, continue to rebuild that H plus gradient, and use up the O2. All right? Next up, oligomycin with the same thing. So oligomycin is going to block ATP synthesis. So essentially what happens, we know this is what happens without ATP synthesis. This is what happens with ATP synthesis. So it makes sense that nothing will happen here. Oh my goodness, bad marker. Okay, why? This is because oligomycin will block, like I said, block ATP synthase. And when ATP synthase is blocked, this also blocks the ETC, right? So the H plus gradient is established, it's not dissipated, and when the H plus gradient is there and it's stable, the ETC stops. Why? Because the ETC and ATP synthase are coupled. What does that mean? It means when one is active, the other is active. When one is inactive, the other is inactive. Okay? So because ATP synthase is not running, that means that there's nothing to dissipate the proton gradient, and therefore the ETC is not active as well. Okay? So nothing to dissipate H plus gradient, and we get no O2 consumption. So because ATP synthase is not there, H plus gradient is stable, that shuts down the electron transport chain, so complex 4 is inactive, no O2 consumption. What happens if we add, instead of oligomycin, antimycin A? So antimycin A is an electron transport chain inhibitor, and we see the same thing. Remember, these are coupled, okay? So with the electron transport chain inhibited, I mean, this is pretty basic. Without the electron transport chain, no O2 consumption, because that means complex 4 is inactive. So ETC plus complex 4 are inactive, no O2 consumption. Okay, so now the last part is we have dinitrophenyl antimycin A ADP phosphate. So dinitrophenyl here, this is an uncoupler. Okay, so what I said here is that ETC and ATP synthase are tightly coupled. When one is inactive, the other is also inactive. Okay, so what we see here is when we add the ADP plus PI, we see the decrease. Even though, oh, I messed this up. This is not with antimycin A, this is with oligomycin. Sorry. My bad. So when the uncoupler is, so this is basically this. So part B showed when the ETC and ATP synthase are both blocked, or when ATP synthase is blocked, the ETC is also blocked. But when we add the uncoupler, we have ATP synthase is blocked or inhibited, but ETC is still active. Why? The uncoupler allows the ETC to run despite ATP synthase being inactive. And that is because uncoupler is going to dissipate H plus gradient without ATP generation. Okay? So it sort of is tricking the electron transport chain into thinking that ATP is being made by dissipating the H plus gradient, much like what ATP synthase would do. But ATP synthase is inhibited, so it's using O2. The ETC is going to be active now because the ETC thinks that there's ATP being made because the H plus gradient is being removed, much like how ATP synthase would do it, but no ATP is being made. So essentially the uncoupler acts like ATP synthase in that it dissipates the H plus gradient, but it does not make ATP, okay? So it's tricking the ETC into thinking that some ATP is being made because all the ETC can track is the H plus gradient, but no ATP is being made, all right? All right, problem 6. So here we're given a list of electron transport molecules that make up some, I guess, newly discovered electron transport chain. And we are first asked, how do the electrons flow between these 6 electron transport molecules? And then we are asked to calculate the amount of ATP generated per every 2 electrons. So essentially the rule to determine how electrons are going to flow is they go from low, so what we're given here is the standard reduction potential. So they're going to go from low standard reduction potential to high standard reduction potential. And what this means is they are going to go from worse oxidant to better oxidant, with an oxidant being an electron acceptor. Okay, so we're going to go from the worst electron acceptor to the best electron acceptor. So that makes sense because in the normal electron transport chain, oxygen is the final electron acceptor. Oxygen would have the highest standard reduction potential, and what that means is that it is the best electron acceptor. Okay, and we know that because it's very electronegative, it really wants those electrons. So if we're going to rank these from low to high, the lowest one here would be ferroprotein B. So that has negative 0.58. And then we're just going to go lowest to highest, so I'm just going to write these out. NADH, cytochrome F, and then goes to flavoprotein. And then it goes to cytochrome X, and it ends at ferroprotein A. And overall, we can just kind of summarize this process as going between ferroprotein B and ferroprotein A, and all the stuff in the middle doesn't matter, because if you actually add together all of these redox reactions that are going on individually, they just cancel out to give you the net reaction between ferroprotein B, ferroprotein A. Ferroprotein B is the worst oxidant, meaning it does not want to accept electrons, it wants to donate electrons. Ferroprotein A is the best oxidant, meaning it wants to accept electrons, it does not want to donate electrons. Okay? So, so now we have to calculate the amount of ATP generated. So, ATP generation, or an ATP is equal to negative 30.54 kilojoules per mole. Don't know if this is given in the problem. It's given in kcal per mole. You'd have to convert between kcal and kilojoules, but just start in kilojoules here. Why not? Okay, so first we have to find the standard, cell potential, so the difference, and then what we do here to find the electric cell potential, the difference in the standard reduction potentials, is we do the standard reduction potential that is highest, or for the acceptor. So this is a high minus the standard reduction potential for the electron donor, which is a low standard reduction potential. So we do the high standard reduction potential minus the low standard reduction potential, or the acceptor, what is getting reduced, minus the donor, what is getting oxidized. If you took Gen Chem, cathode minus anode. But yeah, so we know that the electron acceptor, the best electron acceptor here is ferroprotein A. So here we would do ferroprotein A minus ferroprotein B, because ferroprotein A is the best oxidant, best electron acceptor. Ferroprotein B is the worst oxidant. It's the worst electron acceptor, meaning it's the best electron donor. So if we do this, we get ferroprotein A is 0.77 volts minus negative 0.58 volts. So we get delta E cell, electric cell potential here is going to be equal to 1.35 volts. So now we can use, we have to convert this to energy. Delta G is going to be equal to negative NFE. So F is the Faraday constant, N is the number of electrons, E is what we just calculated, the change in, or the difference in standard reduction potentials. So here what we get is 2. This represents the 2 electrons transferred. So it's asking calculate the amount of ATP generated per 2 electrons. So we put in 2 for N. Don't forget the negative. F, Faraday constant. So it is 96.48 kilojoules per mole volt. And then our voltage, our cell potential is going to be 1.35 volts, right? So putting this in our calculator, we get delta G is equal to negative 260 kilojoules per mole. So now, do I have room to write this? I think I do. So we get now to figure out how many ATP we can make. We know an ATP is negative 30.54 kilojoules, so we get negative 260 kilojoules per mole divided by negative 30.54 kilojoules per mole. Okay, so this is the total amount of energy that we've made, and this is how much energy in an ATP. And if you do this out, you get about 8.67 ATP. So 8.67 ATP can be made from this electron transport chain, assuming no energy is lost. All right, so this is quite a difficult problem, but that is how you do it, and that is sort of the math of the electron transport chain. Question 7, this is very similar to a previous question about the different ways oxidative phosphorylation can be disrupted, but this is a little different. So reduce cytochrome C, so this is going to be cytochrome C plus 2, okay, plus ATP, or ADP plus PI plus O2 is added to the mitochondria. And from this, normal ATP can be made. But we want to know what happens first if we add antimycin A. So we know this is an electron transport chain inhibitor. We saw this in the last problem. So it says specifically, though, this blocks electron transport between Q and cytochrome C. So this is actually happening in complex 3, right? So this does not actually impact complex 4. And remember, we have reduced cytochrome C carrying 1 electron in the solution already. So ATP synthesis continues. Why? Because we have cytochrome C plus 2 is present, and this can go to complex 4, which can then pump 2H plus. Okay, so we're not making a lot of ATP because most of the ETC is shut down, but we can make a bit because complex 4 is still active, and cytochrome C plus 2, the reduced form, it can still enter complex 4, can still pump some protons. Okay, so as long as there's cytochrome C present, ATP production can continue. Okay, what would happen, or what would ATP be made if we add dinitrophenol? So remember, this is an uncoupler. So essentially, this is going to dissipate the H plus gradient. Dissipate H plus gradient. What does that mean? It means we get rid of the H plus gradient. So anything built up, any gradient built up by the electron transport chain, the uncoupler gets rid of it. So no ATP is made. Why? ATP synthase cannot function without H plus gradient. Okay, so the last one, would ATP be made if dicyclohexyl carbodiamide is added. So this is going to block H plus flow through F0. So F0 is the C cylinder. C cylinder of ATP synthase. So this is essentially inhibits ATP synthase, so no ATP made. All right, there is one more part to this question that we can go over. So in each case, indicate the flow of electrons through the system. So here, what's going to happen is this is just going to be complex 4, so 2 cytochrome C plus 2 get oxidized to make 2 cytochrome C plus 3. This one's carrying the 2 electrons here. And then this will go on to reduce oxygen to make 1/2 H2O. You read that? Yeah, the marker's bad, but you can read it. And then part B, this is just a normal electron transport chain, so nothing changes. And so this is normal ETC. Wow, that one's good. Normal ETC. So this is dissipating the H plus gradient, but the ETC is still active. It's still trying to reestablish the H plus gradient. Okay? So ETC tries to reestablish H plus gradient. And then with this one, this is going to stop the ETC. Why? Because this is due to coupling. So no ATP synthase equals no ETC. When one is inhibited, the other is inhibited unless there is an uncoupler present. The uncoupler removes that coupling. Okay? So that is it for this question. Okay. Question 8, almost done. Why do yeast consume less glucose in the presence of O2, and how much? So let's look at this. So without oxygen, we have just glycolysis, right? TCA and electron transport chain require oxygen to function. So glycolysis, we know, gets us 2 ATP per glucose. With O2, we have glycolysis, but we also have citric acid cycle, TCA, tricarboxylic acid cycle, and the electron transport chain. Okay? And this gets us 30 ATP per glucose. Okay? So, as you can see, we go from 2 to 30. So this is a 15x increase in ATP production. Okay? So if we are producing 15 times more ATP, you don't need as much glucose if you have O2 present. So less glucose needed with O2 present to match energy need of cells. So essentially, with oxygen, you're producing a lot more ATP per glucose. So if you think about the cell as needing a fixed amount of ATP to function, if you're producing a lot more ATP per glucose, you don't need as much glucose to hit that goal of how much ATP you need. But if you're only making 2 ATP per glucose, it takes a lot more glucose to generate enough ATP for the cell to function. Okay? So that 15 times increase in ATP production per glucose means that with O2, cells need a lot less glucose to match the ATP need of the cell. So what would be the impact of adding dinitrophenol on glucose consumption? So this, remember, is an uncoupler, and this would increase glucose consumption. Why? We know that this will dissipate the H plus gradient, as we've seen a couple times. Okay? So this will shut down ATP synthase. So why is ATP synthase stopped? It's because ATP synthase needs that H plus gradient to make ATP. Without the H plus gradient, ATP cannot make, or ATP synthase cannot make ATP. Okay? However, the ETC as well as the TCA cycle and glycolysis are all still active, and they will actually increase their activity in sort of a futile attempt to make ATP. So what do I mean by this? So the cell is just detecting low ATP levels. And what do low ATP levels do? They signal the activation of the TCA and glycolysis. A lot of NADH is being made. So the ETC is really active in trying to reestablish that proton gradient. So all of these metabolic pathways are really active. They all detect low ATP. So they're all really hyperactive to try to make more ATP. But of course, that's a futile attempt because ATP synthase is inhibited. No ATP can be made. So they're all basically using up a lot of glucose, right? So uses up more glucose to attempt to make ATP. All right? So they want to make more ATP, but they can't because ATP synthase is inhibited. But in an attempt to make more ATP, they just use up a ton of glucose. Okay? So that is the answer to this question. All right? This is the last practice problem of this practice final. Okay? So given the standard reduction potentials here, how much ATP can be made from this redox reaction? So between Q, ubiquinone, and FAD, so Q has a standard reduction potential of positive 0.04 volts, and FAD negative 0.22 volts. Okay? So let's draw out what these redox reactions look like. So when you're working with standard reduction potentials, you always need to show the reduction reaction. So Q plus 2E minus, we know that 2 electrons are always going to be carried by QH2, right? Plus 2H plus QH2, right? So we know QH2 carries 2 electrons. And then for FAD, we know that FADH2 also carries 2 electrons. So FAD plus 2E minus plus 2H plus FADH2, and this is also carrying 2 electrons. Okay, so these are our reduction reactions. However, one of these is going to be an oxidation reaction. The other will be a reduction reaction. And if you know complex 2, if you remember, FADH2 is going to be what's oxidized and Q is going to be reduced. So from complex 2, we know that we have FADH2 plus Q turns into FAD plus QH2. So the electrons are going to be passed from FADH2 to QH2. Okay? So we now have to calculate the standard cell potential. So E cell, or we can do delta E here, equals E reduced minus E oxidized. This is just as we saw before. I need a new marker. What is being reduced here? So what is being reduced? The QH2 is being reduced. So this is Q. And what is, the Q is being reduced. The FADH2 here is being oxidized. Okay, so this is going to be equal to the standard reduction potential of the reduced species, which is Q, so plus 0.04 volts, minus negative 0.22 volts. So for FAD, we always just work with standard reduction potentials, which represent the voltage change for the transfer of electrons for the reduction reaction. And then when we're calculating delta E, we always just use the standard reduction potentials. However, you still need to know in the reaction which species is going to be reduced and which is going to be oxidized. You can also say that if this is going to be energetically favorable, the species that will be reduced is the one with the higher standard reduction potential, and the one that will be oxidized has the lower standard reduction potential, because this will give us a positive E value of positive 0.26 volts, right? And we know that a positive delta E is energetically favorable, and we can prove that, right? We have to for this problem. So delta G equals negative NFE, or delta E, we could say. So N is going to be 2. That represents the 2 electrons transferred here, all right? And then we are working with, so F is Faraday's constant, so 96.48 kilojoule per mole times volts, or per mole volt, and then our voltage difference plus 0.26 volts, and this gives us a negative delta G of negative 50.2 kilojoules per mole. All right, and then we know from earlier negative 30.5 kilojoule per mole for ATP. So we get the number of ATP produced is negative 50.2 kilojoule per mole divided by negative 30.5 kilojoule per mole. And the result is 1.65 ATP. So what this is showing is that through complex 2, through the transfer of 2 electrons here from FADH2 to Q, we generate 1.6 ATP. And interestingly, that is what we observe in terms of how much ATP is generated per the transfer of the 2 electrons from FADH2, right? It's 1.6 ATP. That's what we calculated from how many spinnings of the C cylinder that would give for how many protons that would pump. So it's really cool to see those values align no matter which way you calculate it, either through the stoichiometry of the electron transport chain and ATP synthase, or from standard reduction potentials. It all kind of gives you the same answer, which is really cool. And that does it for CHEM271 tutorials in this practice final. If you want more practice problems on glycolysis, I have a separate video on glycolysis that has a bunch of practice problems sort of tacked on to the end of that video. So even though there aren't very many glycolysis problems in these 2 practice finals, that is where you will find some glycolysis problems. If you have any questions, you can feel free to email me. My email is attached to this YouTube account. And yeah, good luck on your exams. Thank you so much for watching this series. I really enjoyed making it. So yeah, thank you.